Here's a review for test 2, which is in general covering linear systems, but specifically going to cover frequency response plots or Bode plots, and then the use of Laplace transforms, particularly in solving differential equations. Okay, so I'm going to list first some topics that we'll talk about, and I'm going to break this up into a number of short videos. Okay, so let's talk about having a transfer function. Okay, you should be able to do things like draw a pole zero plot. Okay, you should be able to determine the initial and final values. In this case, it'd be, I guess I'm going to say instead of a transfer function, we'll just call it it could be h of s, okay? Could be y of s, doesn't matter. But initial and final values, then h of t or y of t, right, at time 0 and at time infinity. If you're asked questions about what is the steady state response, you should be able to determine the steady state response to a particular excitation. So typical ones would be like a unit step, or an impulse, or maybe even a ramp, or certainly a sinusoidal excitation. You should be able to determine the low frequency and high frequency asymptotes. Let's see, magnitude and phase asymptotes. Okay, so this doesn't necessarily mean a particular number, but for instance, if you go to very low frequencies, your transfer function could tend toward a 1 over s. Okay, so that would be your asymptotic value. You certainly should be able to write a differential equation from h of s. Okay, and I guess let me take this y of s and y of t off, because that might confuse you for the moment. I did start off by saying let's consider a transfer function h of s. Okay, but if we were given, for instance, some response of a system y of s, I certainly would expect that from y of s you could find the initial and final values of y of t at time 0 and infinity. Okay, and then you should be able to use the Laplace transform to find a particular, to find the, let's see, the complete response. Now in this case, if you're given a transfer function, it's going to actually be the zero state response. Okay, because if you recall, when you take the Laplace transform of a differential equation, there are those initial condition terms that show up whenever you take the Laplace transform of a derivative or an nth derivative. All right, and when we write really a differential equation in a Laplace transform, in a transfer function format, we actually drop those initial conditions, or we assume them to be 0. So if you're given a transfer function and then you're given some input x of t, for which you take the Laplace transform, let's say it's a unit step, it's 1 over s, and so now you're going to say y of s is equal to h of s times, say, 1 over s. Okay, so you should be able to do partial fraction expansion and find the ultimately the inverse Laplace transform using transform pairs and some properties. You should be able to find y of t, and that y of t will be the complete response, but it will be for the case where there's 0 initial conditions. Okay. All right, here's some other things to know. Certainly, you should be able to make. I guess I forgot for h of s. You should be able to create or generate a Bode plot. Okay, so that's going to be both magnitude and phase. Okay, and then let's say given a differential equation, okay, you should be able to take the Laplace transform, right? Take the Laplace transform and express y of s as a function of, we'll say h of s, x of s, all right, plus, and then there's going to be some other terms. We'll do it this way. We'll say there's a numerator, there's a denominator, so this is the transfer function, and then plus some other terms, some IC terms, divided by d of s. Okay, and so you could be asked for the transfer function from the differential equation. So generate transfer function from the ordinary differential equation using the Laplace transform. Okay. Okay, now if you were given a Bode plot, you should be able to do these things. You should be able to generate transfer function, and you should be able to generate a pole zero plot. Okay, and then if you're given